Okay, so in previous lectures we were using the slope y-intercept form of a line, which looked like this. That's slope y-intercept, slope y-intercept form of a line. But that's not the only way that you can write a linear function. And so we're going to look at another form of a linear function right now. And this is called the point-slope form. And the name is very important because it tells you the things that you need to use it. So here we go. Given a point x1, y1 on a line with slope a, the point-slope form of the line is given by y equals a times x minus x sub 1 plus y sub 1. Below, we've written this in proper function notation. F of x equals a times x minus x1 plus f of x1. So let's talk about what all these symbols mean. Let me actually draw a picture. I think that will be a good way to motivate this expression. So here we have an xy axis. And let's say we have some point here. This is a particular point, and it's going to have the coordinates x1 and y1. Okay. Now, let's say that we have a line that goes through that point, and that this line has slope a. Okay. Then the equation of the line going through this point with this slope is given by this expression, where x and y are the variables, the input and the output, and x1 and y1 is the fixed value. Okay. So with that in mind, let's go back to our PowerPoint. And let's look at an example where we'll actually use this, because we need to understand in what scenarios we would want to use point slope versus scenarios where we would use ax plus b. Okay, so here's an example. A city had a population of 375,000 on July 1st, 2000, and was growing at the rate of 9.25 thousand people each year. Assume the trend continues. Find a formula that gives the city's population in thousands as a function of the calendar year. All right, and notice there's an asterisk here. So where an integer year represents the midpoint July 1 of the given year. Okay. So what does this mean? Well, we've got this piece of information. We have this piece of information. So what do all these things add up to? So 9.25 thousand is your change. It's your rate. So notice that that's a rate. So this is actually your slope right here. This is your slope. We know the initial population. Okay. And we know when that initial population occurs, which is July 1st, 2000. So if this said as a function of elapsed time since July 1st, 2000, or a function of time since July 1st, 2000, then we would use ax plus b. So actually, let me write that down. So if it says as a function of time in years since July 1st, 2000. So if that was what the problem said, then I would use ax plus b, and my formula, or my line, would be 9.25x, or t, plus 375. Okay, so 9.25 is my slope, 375 is my population, and this is the initial time. Okay, but notice that the problem doesn't say this, right? It does not say as a function of time in years since July 1st. What it says is a function of calendar year. Okay, and that is different. So what that means is that what the question is asking you is to write a model where you actually input the full calendar year, like 2000, 2001, etc. Okay, and in those scenarios, you're going to use the point slope form of the line. So what we would want to do here is instead write y equals, let's write the form down, x minus x1 plus y1, and x1, y1 is the point 2000, comma, 375. So it's actually the calendar year 2000 is x1, and y1 is the initial population. And our slope is still 9.25, but our model is now going to be 9.25 times x minus 2000 plus 375. And so that is the calendar year model. Okay. In many ways, it's equivalent to this model. They're not the same, but they're certainly connected. How they differ is they're basically parallel to one another, but this lower model, the calendar year model, is kind of offset. It's way over. In fact, I can draw it. If we graph both of these lines, the point slope one would be like over here, and that would be 375 right there, 0, 375. But the calendar year is going to be way over here, and that same point that's at the same height, it would now have coordinates 2000, comma, 375. So this is the calendar year, and this is the elapsed time model. So when I say they're parallel, that's exactly what I mean. They are parallel in this regard. Okay. Which brings a couple of points up. The y-intercept for this one, the y-intercept doesn't have the same meaning as it has for the slope y-intercept form, because the slope y-intercept form, the y-intercept is the initial population, but here the y-intercept is not the initial population. Okay, so that's going to be relevant in some questions, so remember that. Okay, so getting back to our question, parts B and C are where we're actually going to use the model a little bit. So in part B, it says, according to the model, what was the city's population on July 1st, 2010? All right, well, this is a simple type 1 question where we want to evaluate the function at a given input. So that's a vars y vars question. So bring up the calculator, and we need to clear all this and then input the function. So our function is 9.25 parentheses x minus 2000 plus 375. Okay, so we've entered the function now, and if I want to evaluate that function for 2010, that's going to be vars y vars function y1. And now be careful here, don't put in 10. You actually put in 2010 here, because that's the calendar year model. The inputs are actual years. So don't make that mistake. So our output is 467.5 thousand. Okay. All right, for part C, use the model to predict the year when the population will reach 600,000. This is a type 2 question, so we're going to use calc intersect. Okay, and what we will be intersecting is 600, which represents 600,000. Okay, now, but we're going to need to think about the window here, because with a calendar year model, remember this picture that I drew a moment ago, it's offset, it's way over here, right? And so our window needs to reflect that so that we actually can see it. Now what that means is that our X min and X max needs to actually reflect the year values. So if we're starting in the year 2000, well, I think I might actually go back a little bit to like 1995 or 1990, just so I can kind of get the picture centered a bit. And then for my X max, I don't really know. Let's go 2020. And then we can do the table and see if that will do it or not. Now notice with the table, now we're really going to have to change our table setting because we're way off. So I'm going to go to table set, and I'm going to start the table at 2000. And I'm just going to go in increments of 1 here. So I'll go back to my table. And I'm looking to see when I get to 600, and not too far down. There we go. So 2024 to 2025. So I didn't have my window big enough. I put 2020 here, but I should actually probably make this like 20. Let's make it 2040. And then we'll do zoom fit. So the 2040 was just a rough guesstimate. Okay. But this should now get me, at least I can see the intersection. There it is. So that's actually a pretty good graph. So now let's do second trace, calc intersect. First curve, enter, second curve, enter, and then my guess, I'll move over here, enter again, and notice what it tells me. It actually gives me the year, so it says 2024.32. Okay. Now the nice thing about calendar year is that I don't have to figure out the calendar year anymore because it gives me the answer in that form. Now the only thing I do need to worry about is if the decimal portion is big enough to push me into the next year. And remember that you're starting in July. This is not, though, because 0.32 is still less than 0.5, so I'd still be within 2024. Okay. If you got lost in any of that, here's a slide that explains this in a little bit more detail, so I encourage you to look at that. And there's our answer. Right here. All right, so that's a little bit about using the calendar year model. Both of these are examples of linear behavior, and any fixed change in the independent variable of a linear function results in a constant change in the dependent variable. That's what slope means, right? So constant slope, I mean. So for a fixed change in the independent variable of 1 unit, the resulting constant change in the dependent variable equals the slope. Okay. So the point here is that for a line, if you want to find the slope, you go over 1 unit and see how far up you go. Basically, you could say if you set your run to be equal to 1, then the slope and the rise are the same value. Okay. Now to kind of summarize what we just did, well, actually, we'll pick this up in the next video. Okay.